I'm going to be talking about fast rates for no regret learning in general games. This talk is going to have two parts. In the first part, I'll discuss a couple of papers that get near optimal rates for no regret learning in finite games. This is based off of two papers. And in the second part, I'll discuss how we can extend some of the results to the setting of infinite or more generally non-parametric games. And the results in this talk are based off of joint work with many great co-authors. Nowadays, modern machine learning applications are multi-agent in nature. Consider, for instance, generative adversarial networks, where you have a discriminator and a generator competing against each other with the goal of attempting to generate images from some natural distribution. There's multi-agent reinforcement learning, where multiple agents compete with each other, each trying to optimize their own reward function. And there's also adversarial examples, where on the one hand, there's a classifier attempting to correctly classify images. There's an adversary that attempts to corrupt the output of that classifier. Now, we have a lot of successful approaches, both in theory and in practice, for single agent machine learning. But when we try to extend these to the multi-agent setting, often they break completely, or they become at least more unstable or brittle. And so an important question is, what needs to change in our approaches for single agent learning to achieve comparable success in the multi-agent setting? So to begin to address this question, I'm going to consider a really simple multi-agent setting, which is finite normal form games. So really consider the repeated game setting. So agents play a general sum game repeatedly over a finite time horizon. And this can be used to model many real-life applications, such as auctions, repeated bidding in auctions, or playing in network routing games. And an important question in this setting is, how do we model agent strategies over time? So one idea is to assume that agents can compute a Nash equilibrium up front and then play according to the Nash equilibrium at each of many time steps. Unfortunately, this hypothesis is, first of all, problematic because it's computationally hard to compute a Nash equilibrium even in finite normal form games. And it's also not supported by some empirical evidence, which indicates that agents often don't play according to Nash equilibrium. The second hypothesis that we'll consider is to assume that agents update their strategies over time according to some simple online learning algorithm. When we do this, the most fundamental and important question is, does this algorithm converge to equilibrium? And if so, how fast? So I'm going to give a little bit of background on online learning in games. It dates back well over half a century to Brown's work on fictitious play, Blackwell approachability, a non-consistency, and many other works. And one of the most desirable properties of an online learning algorithm is that it be no regret. So we say that an algorithm is no regret if each player's regret, or the difference between their cumulative loss and the best possible loss they could have achieved in hindsight, is sublinear in the horizon t, the number of time steps t. And there's many popular no regret learning algorithms that have been well studied over the years. Some of them are listed here. But first of all, why do we care about regret? Well, first of all, it's a very natural notion. But second, if it has a nice property involving equilibrium, convergence to equilibrium. If an algorithm has regret at most some function epsilon of t, then the empirical averages of the algorithm's joint action profiles over time, when all agents play according to the algorithm in a game, converges to a type of equilibrium known as coarse correlated equilibrium at a rate of epsilon of t over t. For those of you who are unfamiliar, this is a superset of Nash equilibria, but unlike Nash, it's computationally feasible to compute them. And what's nice is that all of these no regret learning algorithms have regret that grows on the square root, the order of the square root of the horizon t. So what that means is that gives convergence to coarse correlated equilibrium at a rate of 1 over root t. And this rate of over root t is known to be optimal against the worst case adversary. But there's an important thing to note here, which is that in games, agents are not facing worst case adversaries. They're facing other copies of their own algorithm playing against them. So the question that we're going to address in this talk is, can this worst case adversarial regret of root t be improved if we use that all agents in the game are playing according to a no regret learning algorithm? And the answer to this question is yes. But to explain exactly what the results are, I need to first formally introduce our model. We work in the following setting. We assume that there's M strategic agents. You can think of these as, for instance, bidders in an advertising auction. And each agent I has a finite action set AI. The product of these agents' action sets is A, which is the A1 times A2 all the way up to AM. That's the joint action set. And each agent I has a loss function, which is a mapping from the joint action set to a real number between 0 and 1, given agent I's loss, if all agents play according to some given joint action profile. So here's the setting we consider. For each time step t, each agent I chooses a strategy SIT, which is a distribution over their actions. But think of this as a vector lying in the simplex, distributions over AI. And the collection of strategies ST, which is the concatenation of the individual vectors S1t through SMT, determines a loss vector for each agent I. The number of entries in this loss vector is the number of actions. The AI entry of LIT is simply the expected loss of agent I if they play according to the action AI and others draw their actions from the distribution ST. So here's the same thing written out in notation. We're just looking at an expectation over this distribution of agent I's loss function. Now, finally, each agent I suffers a loss, which is the expected value of their loss function over the distribution ST. And this can be seen easily to be equal to the inner product of their strategy vector SIT and the loss vector LIT. After suffering this loss, the agent I observes the loss vector, which tells them how to improve their loss, improve their strategy in future iterations. So this is basically, from agent I's perspective, equivalent to the setting of online linear optimization with full information feedback. Now, each agent I's goal is to minimize the regret, which is the difference between two terms. It's the aggregate loss of the algorithm that they're playing and the best possible loss in hindsight they could have achieved by playing a single fixed action in their action set. And of the many no-regret algorithms I mentioned a couple slides ago, a particularly important one is Hedge, otherwise known as exponential weights. It's a very simple algorithm. The iterates are shown here. So in the first round, agent I plays a uniformly random action from their action set. And in the subsequent rounds, each agent I updates their strategy vector according to the formula shown here. In particular, to get the strategy vector at time t+1, you take that at time t, and you reweight it according to an exponential of minus step size eta times the loss at time t for each action. Now, this is a very natural formula because actions with higher loss are going to be downweighted by a larger amount in subsequent iterations. Now, the regret hedge is known to, against the worst case adversary, scale as a constant times the square root of t times log number of actions. And this regret bound is tight against an adversarial loss. That's a well-known result. But it turns out that it's also tight in the game setting. In particular, Chen and Peng showed that in the game setting, the regret can scale as a constant times the square root of t when all agents use Hedge. Now, this is a somewhat disappointing result because we want to be able to improve these root T regret bounds in games. The good news, though, is that there's a slight modification of Hedge known as optimistic Hedge, which can get better regret bounds. So how does it differ from Hedge? It only differs in this reweighting term. Previously, we had the term shown here. But in optimistic Hedge, we have an additional thing we're adding on, which is the loss vector at time t minus the loss at time t minus 1. And this additional component of the optimistic Hedge update rule can be thought as a sort of prediction of the losses at time t+1. It turns out that what you can show fairly generically is that if the losses that optimistic Hedge encounters are predictable in the sense that it achieves improved regret bounds over those of Hedge. And a lot of the work about showing optimistic Hedge gives better rates in games is showing that in some sense, the loss vectors are indeed predictable. Now, optimistic Hedge also gets this same worst case adversarial regret bound as Hedge against an adversary. But as I've said, this can be improved in games. Okay, so how exactly, how much can this regret bound be improved by if all agents use optimistic Hedge? Here's our main result. So for simplicity in stating things, I'm going to assume that each player has the same number of actions. And so the cardinality of the joint action set is the cardinality of an individual agent's action set to the mth power. And what we show is that if agents with joint action set A play a general sum game over T rounds, and each player uses optimistic hedge to update their strategy, then the regret of each player is a constant times logarithm of the number of actions times log of T to the fourth. Okay, now ours is not the first result that gets fast rates for learning in games. To kind of explain the context, I'll briefly overview some prior work on this problem. So after in addition to the worst case regret of root T, it's been known for over a decade that in the two-player zero-sum game setting, there are several specialized algorithms which can get polylogarithmic regret in T in the number of actions. Now, two-player zero-sum games are in many respects much easier than general-sum games. One important respect in which they're easier is that optimistic algorithms, such as optimistic hedge, actually exhibit last iterate convergence to the Nash equilibrium. And this last iterate convergence makes it, in a rough sense, easier to prove fast rates. And correspondingly, the fast rates that have been known in multiplayer general-sum games have lagged behind those in two-player zero-sum games. So in 2015, Serganis et al. Showed a regret bound that scales as T to the minus 1/4. That was improved to T to the 1/6 by Chen and Peng in 2020. And our result was the first to get a polylogarithmic regret bound in T for multiplayer general sum games. And subsequent to our work, there's been a new paper which shows that a different algorithm called clairvoyant MW gets regret that's constant of the time horizon T, although they work in a slightly different setting of multiplayer general sum games with free rounds of computation. Okay, so now I'll give one slide overviewing the proof of our main theorem. There's two main lemmas in the proof of our main theorem. The first is shown here. It gets what's known as a path length regret bound against an adversarial. So what we show is that for an adversarial sequence of losses, agent I's regret is bounded above by the sum of three terms. The first term is relatively mild, it's just log of number of actions over step size. The second term is a sum over each time step T of the difference between loss vectors in consecutive rounds, measured with respect to a particular local norm. And the local norm we use here is mentioned at the top of the slide. You don't have to worry about it. It's not that important for the purposes of this slide. And there's a third term which is negative. So it's going to help us make the regret bound smaller. It's a sum over time steps T of the loss vector at time step T, measured again with respect to this local norm. And so this lemma is relatively standard. It's similar things to it have been known for a while. We do have to modify the existing work a little bit, but that's not the bulk of the proof. The bulk of the proof is actually the second lemma, which shows basically that the sum of the blue terms in lemma 1 are bounded above by the sum of the red terms. And combining these two lemmas gives a polylogarithmic regret bound almost immediately, because lemma 2 says we can replace the second two terms of lemma 1 with basically something that's polylogarithmic in T. And that gets what we want to, assuming the step size is chosen appropriately. So lemma 2 is the bulk of the proof. I'll give you a little bit of intuition as to why it holds. We want to show the blue terms are small. Now, this actually has precedent in the literature. Serganis et al. Showed that the blue terms are small in an absolute sense. In particular, they showed if the step size is chosen small enough, then the blue terms will be small in comparison to that step size. Of course, we can't make the step size too small because of this first term in lemma 1. And to show lemma 2, we really have to show that the blue terms are small in a relative sense. But this isn't obvious. What if the blue terms are small, but the red terms are even smaller? So let's work through this a little bit. What happens if some loss vector lit minus 1 is small compared to the blue term at the same time step? Well, suppose that we can show that the differences, the loss vectors, these blue terms themselves change slowly as a function of time. And it turns out that eventually the red terms will become large. So in particular, say loss vector L1 is quite small. We have some arbitrary difference of loss vectors, which gives some loss vector Li2, which might be a little bit larger. But if the blue terms don't change that much, we're kind of adding roughly the same direction to these vectors over time. Because we're adding roughly the same direction, the loss vectors themselves, the red terms, will eventually become large. And that's good because that basically allows us to show something like lemma 2. Okay, so now that's kind of the idea of the proof. I'll now discuss some extensions of our main results. So here's one extension. We call it our main theorem gets a bound on the regret of each agent. This is otherwise known as external regret. And it's nice because it complies convergence to a type of equilibrium known as coarse correlated equilibrium. Now, there's a more fine-grained notion of equilibrium known as correlated equilibrium, which also contains all Nash and is computationally feasible to compute. Unfortunately, regret bounds are not enough to get convergence to correlated equilibrium. We need convergence of a stronger notion of regret known as the swap regret. So I've defined swap regret here. Roughly speaking, it's similar to regret, but the comparative term shown in blue is a little bit different. We're now taking a minimum over all functions pi from the action set of AI to itself. We're going to call such a function a swap function. We're going to look at the aggregate loss in all t rounds of the following. Consider any round where agent I plays any action A. We're going to consider the loss of that agent if instead they played action pi of A in that same round. And we do this for all rounds and all actions. And taking the minimum over all possible swap functions where they swap from one action to another gives us this blue comparative term, and that defines the swap regret. The swap regret is enough to get convergence to correlated equilibrium, and we can show a corollary, or sorry, we can show an extension of our main theorem that holds for swap regret. So in joint work with several co-authors, we've shown that if each of many players uses a no swap regret algorithm, in particular, a particular algorithm by Stoltz and Lugosi combined with optimistic hedge in a certain way, then each player I gets swap regret that scales as the number of players times the number of actions times log of t to the fourth. Now, there's another no swap regret algorithm literature by Blum and Mansour, and a similar result holds for their no swap regret algorithm combined with optimistic hedge, albeit with a slightly worse polynomial dependence than the number of actions. And it's an interesting open question as to whether or not this linear dependence in the number of actions can be improved. For our results on regret or external regret, we're able to get logarithmic dependence in the number of actions. Linear is known, or polynomial is known to be necessary in the adversarial setting. We don't know if that's the case in the game setting. Okay, so that concludes the first part of the talk. In the second part, I'll move on to discuss how we can get fast rates for regret in infinite games or non-parametric games. And to motivate this, I'm going to go back to some of the questions I discussed in the first slide. There's many challenging non-convex multi-agent settings, such as multi-agent reinforcement learning, learning in generative adversarial networks. And these, of course, are not finite normal form games. They can be expressed as infinite normal form games, where you take the space of actions AI of each agent to be, say, the space of all weights of a neural network. And this is a pretty daunting thing to do. It's kind of hard to work with instead of all weights of a neural network by using optimistic hedge over them in the way that we did in the first part of the talk. So what prior work has done in terms of equilibrium computation in such settings is to, for instance, look for local notions of equilibrium. Unfortunately, there's many intractability or non-existence results. So one type of equilibrium known as pure strategy local Nash equilibria may not exist even in two-player zero-sum non-convex games. There's a generalization of such a local Nash equilibrium known as local approximate pure strategy Nash equilibrium. Those do exist because they can be phrased as the fixed point of a continuous operator in a compact space. But unfortunately, they're p-pad hard to compute. This is shown by Daskalakis, Skoulakis, and Zampatakis. So we're going to do something a little different. We're going to say, well, local equilibria have these issues. Let's look instead for global mixed Nash equilibria. These are just mixed Nash equilibria of this infinite game. And that's in the two-player zero-sum game setting. More generally, in multiplayer general sum settings, we can look for global coarse correlated equilibria. Of course, when we do this, there's going to be an elephant in the room. global equilibria in non-convex settings are going to be computationally intractable. Even in a single agent setting, optimizing a non-convex function is computationally intractable. So how do we deal with this? Ultimately, I think one strategy is to try to define some oracle which has efficient heuristics in practice, although those may not be provable. We want there to be an oracle efficient algorithm for this oracle. Now, this is not a question we address in our current paper. It's left for future work. And I'll discuss some directions along these lines further at the end of the talk. But I think it's important to understand the basic statistical questions before moving on to the computational ones. Okay, so learning in large infinite games, how do we do this? Well, let's consider a two-player zero-sum game with infinite action spaces. You can think of these as, for instance, action space is the space of all weights of a neural network. There's a few questions we want to consider. The first is whether Nash equilibria exist. Of course, those local notions of equilibria I mentioned a couple of slides ago may not exist. So if we're going to try to get around these issues by considering a different notion of equilibria, we should make sure it exists. Second, if Nash equilibria do exist, then at what rates can we get convergence to them? We'll in particular consider no-regret algorithms. Now, this question has actually mostly been answered by prior work in the literature. For instance, it was shown by Rachlin, Swihart, and Tewari that under a particular compactness assumption, which guarantees the existence of Nash equilibria, you can get an algorithm that achieves essentially optimal rates for non-parametric classes against an adversary. And the work more or less generalizes to hold under any setting in which we can show a min-max theorem. But of course, analogously to, as I discussed earlier in the talk, we're not really content with worst case adversarial regret in games. We want to somehow use the fact that agents are playing in games to get improved regret bounds. So typically, these worst case regret bounds will scale as the square root of the time horizon. When I say fast rates, I want something that's less than root t. Okay, so I'm now going to discuss our answers to the first and third questions on this slide. Of course, the second has already been answered. The first question on the existence of Nash equilibria in infinite games, unfortunately, has a negative answer. Nash equilibria may not exist in infinite games. And if you've seen this result before, chances are you've seen a particular counterexample known as guess the larger number. So here's the game. It's a two-player zero-sum game. The action spaces of each player is the space of all natural numbers. And the rules of the game are very simple. Whoever guesses the larger number wins. Let's break ties, say, in favor of the max player. Now, if you think about this for a couple of minutes, you'll quickly see that this infinite two-player zero-sum game has no approximate Nash equilibrium, even up to a constant approximation. So Nika talked about this in her tutorial a few weeks ago, so I won't go into the proof. But it's a very simple proof. There's really not much to it. So this is somewhat disappointing. We want Nash equilibria to exist. But there is a glimmer of hope, which is that probably none of you have seen any other counterexamples. There's a reason for that, which was that in a really nice result by Haneke, Livni, and Moran last year, they showed that basically this guess the larger number game is the only obstacle to having a Nash equilibrium. In particular, if an infinite binary game is no subgame, which is isomorphic to guess the larger number, then this infinite binary game is approximate Nash equilibria for any positive approximation. Now, this condition of not having any subgames which are guess a larger number is a very clean condition to state, but unfortunately, it's not that operational. A slightly more convenient condition to work with, which is sufficient for this subgame condition, is that those games with finite Littlestone dimension have no subgame that's guessed a larger number and therefore have approximate Nash equilibria. Now, for those of you who aren't familiar with Littlestone dimension, I'll define it in a couple of slides from now. But for now, you can think of it as an online learning analog of the VC dimension, the parameter which characterizes online learnability. Also note that having finite Littlestone dimension is in a certain, somewhat vague sense, almost necessary for not having any subgames which are guessed a larger number. So our first result is we extend the result by Haneke, Livni, and Moran to the real valued setting. In particular, what we show is that if an infinite real valued game has no subgame, which is close to some affine transform of guess the larger number, then this game has epsilon approximate Nash equilibria for all positive epsilon. And by affine transform, I simply mean you take entries to guess the larger number, you shift them, you scale them by a positive constant, and then you shift them. Okay, so both of these theorems have what's essentially a converse, in particular, what Haneke, Livy, and Moran showed, and what we can show is that a necessary and sufficient condition for a game and all its subgames to have Nash equilibria is that they don't contain some copy or approximate copy of guess the larger number. Okay, so that basically answers the question of equilibrium existence. So let's move on to our second main question, which is that can we get fast rates for learning in games? And I'll focus on games of finite Littlestone dimension. Of course, by the condition on the previous slide, for these games we're on solid footing. We know that Nash equilibria exist. So here's our main result. We show that there's a no regret learning algorithm, that if each player uses it, then the regret in games scales as t to the 1/4 times a polynomial in Littlestone dimension. And this holds even in general sum binary valued games. This gets the fast rates that we wanted. The important thing to note is that it has no explicit dependence on the number of actions, unlike basically all prior work getting fast rates for learning in games. In particular, the dependence of the number of actions in the prior work is logarithm of the number of actions. This result it can be viewed as a sort of improvement upon that, because Littlestone dimension is always bounded above by the logarithm of the size of the action space. Of course, there is one part of this result which isn't that strong, which is the polynomial dependence on t. Of course, in the finite game setting, we can get something down to polylogarithmic in t. It's open as to whether or not that's possible in the general sum game setting. Yeah.
So for non-fast rate, square root t, what was known?
So the question is for non-fast rates like square root t, what was known? So you can get root Littlestone dimension times t.
Okay.
Oh yeah, yeah.
So the Littlestone dimension depends on the payoff.
Yes, Littlestone dimension. Yeah, I'm going to define it in a minute, but it depends on the payoff matrix. Yes, it's a measure of complexity. Okay, so as a correlate of this theorem, we get the expected results about convergence to equilibria. In particular, in two-player zero-sum game setting, we get convergence to approximate Nash equilibria. And in general sum game settings, we get convergence of the joint action profiles averages to coarse correlated equilibria, both at a rate of t to the minus 3/4. And this improves upon the rate of 1/root t that you get from the adversarial setting. Okay. So now I'll discuss the proof of this theorem. The proof is quite long, and there's several ingredients in it. Roughly speaking, these are ingredients really apply to the more general setting of adversarial online learning, the non-game setting. And I think several of them are of independent interest, so I'll try to give an overview of the ingredients that I think maybe have applications in other settings as well. So first of all, we get fast rates for proper online learnings in a setting of online learning known as the realizable setting. I'll define what this is in a moment. We show how to make our proper online realizable learner stable. And finally, we show how to use that proper online stable learner to get a path length regret bound in the non-realizable setting. So I'll explain what all these things mean. But first of all, I need to define what the Littlestone dimension of the game is. So consider, as before, a binary valued game G. And the loss function of agent I is denoted by Li. It's a function of the M agent's actions. Now, these action spaces AI we're going to consider the setting now where these are extremely large or infinite. So unlike the first part of the talk where we use the size of the action sets to measure complexity, we don't want to do that anymore. We want some other measure of complexity. And the way we do this is as follows. We're going to define a bunch of function classes, otherwise known as hypothesis classes, associated with the game. There's one for each agent. And the hypothesis class for agent I, denoted by HI, is this class of functions right here. It's indexed by actions AI of agent I. And for each such action AI, there's a function in the class HI, which maps the actions of all other agents to the loss of agent I when they play according to their actions AI and A minus I. So this is a sort of induced hypothesis class from the game, given by agent I's loss function on all possible actions of agent I. Now we define the Littlestone dimension of a game to be the maximum of the Littlestone dimension of any of these hypothesis classes HI. But of course, I haven't told you what the Littlestone dimension of a hypothesis class is. So in general, for a class HI of hypotheses mapping from the space of joint actions of other agents to 0, 1, there's a complexity measure of it corresponding, known as Littlestone dimension. And to define what this is, I'm now going to move away from the game setting to the setting of adversarial online learning. So there's a little bit of a context switch here. We're now going to be talking about the adversarial setting. In the adversarial setting, I'm going to actually generalize notation a little bit. I'll fix a space X. So in the game setting, this would be A minus I. I'll also fix a hypothesis class big H of hypotheses H, which map from X to 0, 1. These are binary hypotheses on X. And we consider the setting of adversarial online classification. So at each time step little t from 1 to capital T, we have the following scenario. The learner chooses a hypothesis HT mapping from the space X to 0, 1. This hypothesis HT need not lie in the class big H. And the adversary chooses a pair XT, YT consisting of a point in the space X as well as a binary label. After choosing them, the learner and the adversary reveal their choices to each other, and the learner suffers a loss, which is the difference between HT of XT and YT. So this loss is 1 if the learner incorrectly predicts the label of YT given XT, and it's 0 if the learner's prediction is correct. Now there's a constraint that we're going to place in the adversary, which is known as the realizable setting. In particular, we constrain the adversary to choose their examples XT, YT, so that they're all consistent with some hypothesis H star belonging to the class big H. In a realizable setting, the definition of regret collapses to what's known as cumulative loss or mistake bound, which is simply the sum over all time steps of the loss of the learner. This is because that comparative term in the definition of regret is 0. The Littlestone dimension hypothesis class is the smallest positive integer d. So there exists an algorithm whose mistake bound or cumulative loss bound is at most d, and this holds against any realizable adversary. So some of you may have seen Littlestone dimension defined in a different way, namely as the depth of the largest tree, which is shattered by the hypothesis class. This definition is equivalent, and that was basically the main, one of the most well-known results of Littlestone's paper back in the 80s. This definition, this algorithmic definition, is a little more convenient for the purposes of this talk. And in particular, I'm now going to discuss our first main ingredient of the proof, which can be seen as correcting a certain issue with the setup of learning I had on the previous slide. So in the next few slides, I'll kind of have a little box in the upper right-hand corner, which reminds you of the choices the learner and adversary make at each iteration. Recall in the previous slide that the choices HT of the learner did not have to lie in the hypothesis class big H. In other words, such algorithms are known as improper learning algorithms. A proper learning algorithm, in contrast, is one that requires that HT belongs to H. And perhaps surprisingly, in many settings, proper learning is strictly harder than improper learning. This holds both in a computational sense and also in a statistical sense and for various problems. In fact, there are problems that proper learners cannot solve, but that improper learners can solve. Unfortunately, we actually need proper learning algorithms for our applications in games. This holds roughly because proper learning algorithms are those which choose, roughly speaking, valid actions. Here's our main. Here's one of our results. We show that there's a randomized proper learning algorithm that achieves a cumulative loss bound, which scales as this quantity shown here against any realizable adversary. We called it for improper learning algorithms. In the previous slide, the loss bound, the mistake bound, was just Littlestone dimension. The amount here we get a bound which is a little bit worse. It's off by a logarithmic factor, a polylogarithmic factor, the time horizon. It's an interesting question to see if you can get this all the way down to Littlestone dimension, but really it kind of gets it's the first result that gets fast rates for proper learning against a realizable adversary. In particular, the best known regret bound prior to this was on this order of the square root of Littlestone dimension times t. So it's the first, it basically improves root t down to polylog t. Yep.
Okay, so if you have like log t, the previous result was t to the 1/4, right? So previous result for the more general setting.
You mean which previous result?
When both players play.
Right, so that's in the game setting. Like that's not realizable. I mean, so those are disjoint settings.
It's not reliable. Okay.
Yeah. So the question is about the previous
The
result.
game setting, it's not reliable.
The game setting. So that's not realizable. And I'll discuss how we use the Brooks results in realizability to get results in the non-realizable setting in a couple of slides. But this is a different setting than the game setting. It's against
It's
the
not
adversary.
reliable because it's non. You can get non-zero logs, right?
Yes, the game setting is non-realizable because there doesn't necessarily exist an optimal hypothesis in your class that classifies all the examples correctly in the game setting. But yeah, so the realizability setting is used for the game setting. But, yeah, good question. Okay. Now, one other thing I'll mention is that randomization is actually necessary to get a sublinear regret bound for proper learning. So we can't make this thing deterministic. We also have an extension of this theorem to the real values setting. And finally, I'll note that the technique is fairly complicated. The algorithm is somewhat complex, but it follows this framework of Haneke, Livni, and Moran. It's kind of an explicit constructive algorithm in a certain sense. Okay, so moving on from proper learning, there's one additional constraint that we need to place on our proper learner, which is known as stability. So I define a proper learner to be stable, eta stable for some positive real number eta, if the consecutive hypotheses the proper learner outputs, ht and ht plus 1, are distributed according to distributions that have total variation distance at most eta. So informally, this is just saying that the outputs of the proper learning algorithm don't change much from round to round. And we can actually show an extension of our result on the previous slide to get a eta stable proper learning algorithm. In particular, for any eta, there's such an algorithm that gets a mistake bound at most 1/eta times the loss bound from the previous slide. And this holds against any realizable adversary. So how do you get an eta stable proper learner? It's actually very easy. You just take the learner from the previous slide and you average the last 1/eta consecutive hypotheses it outputs. And this is immediately seen to be eta stable because you're only changing mass eta from iteration to iteration. The more challenging part is to get this loss bound. And it seems very natural to get the scaling on 1/eta, but it's actually not immediate. It doesn't work in general. And in fact, if you're not careful about averaging, you might get a cumulative loss linear in T. And so in order to get this bound that's very much sublinear, at least for reasonably sized eta, we have to do a very careful analysis of the explicit construction of the proper learner I had on the previous slide. I think this result may have some independent applications. Stability in learning has been studied in many other settings as well. Okay, so finally, I'll move on to the final intermediate result we need to get for our result on fast rates in games. I'm now going to move beyond the realizable setting to the non-realizable setting. And we call it in a non-realizable setting, the aim is to minimize regret as opposed to cumulative loss. And what we show is the following. There's a randomized proper learning algorithm, which is also stable. I'm now setting the stability parameter to t to the -1/4. And this satisfies the following. if for all time steps t, the adversary chooses examples xt and xt plus 1, which are close to each other in a certain sense I won't define formally here, then the regret of the algorithm is t to the 1/4 times a polynomial in Littlestone dimension. So this is exactly the sort of fast rates that I claim in games. But it's under this condition, which is not realizability, but it's a certain closeness of the adversary's examples. Now, the proof of this result actually uses the proper stable learner from the previous slide. It's a relatively standard technique, and here's how it goes, roughly speaking. We're going to construct what's known as a sequential cover of the hypothesis, which consists of proper stable realizable learners. And we're going to use elements of this sequential cover, which for now you can just think of as different algorithms, different online learning algorithms. We're going to use them as experts and plug that into optimistic hedge. I won't go into detail into what this means too much, but I'm just going to say that optimistic hedge gives us a fairly generic way of getting fast rates, as long as these experts, these individual algorithms, don't change much from round iteration to iteration. And this is exactly why we need stability. It's to get it's basically be able to plug into optimistic hedge, which then spits out fast rates for us. Okay, so what this means is that once we've proven this theorem, all we have to do in order to get fast rates in the game setting is to show that from each agent's perspective, the effective adversary given by all other agents' actions at each time step leads to examples that are close to each other up to this approximation of t to the -1. This actually holds quite immediately in the game setting, again, by the stability property of this randomized proper learning algorithm. And so this is the second place it needs stability. Stability is really crucial in the proof of this result. And that's how we get fast rates in games. Basically, it's an immediate corollary of this path length regret bound. Okay. So I'll finally conclude. There's a lot of different notions of equilibria out there in the literature. In the setting of generic non-convex games. On the one hand, there are these notions of equilibria, which are local in nature that I discussed earlier on, namely pure strategy, local approximate Nash, and pure strategy, local Nash. Unfortunately, they're either computationally hard or do not exist sometimes, respectively. Now, the results of our work can be seen as lying on the opposite end in this local global spectrum. We're looking at global equilibria, and as we show following prior work, they do exist, and actually we can get fast rates for convergence to them. Now, these rates are statistical in nature. Our algorithm is not computationally efficient in any way. Oracle efficiency is a really interesting open question. Unfortunately, there are some negative results in the literature on Oracle efficiency. So Hazan and Karan show Oracle lower bounds for computing Nash equilibria, even in two-player zero-sum games, with an ERM or empirical risk minimization Oracle. This is fairly disappointing. It basically tells us that you can't get efficient Oracle efficiency with respect to this Oracle. But there may be some extensions of this Oracle for which you can get Oracle efficiency, or there may be additional assumptions that you can place, or beyond worst case assumptions you can place on your game, once again, in order to surpass these Oracle lower bounds. So that's one interesting direction. Another is to kind of explore this space in the middle between local and global. So there actually are some positive results in the literature. In fact, a few of them I think are going to be discussed later on in this workshop. And some of these notions of equilibrium can be seen as somehow being mostly local in nature, but having some maybe global aspect to it. And I think kind of this middle ground, finding stronger middle ground notions of equilibria that also satisfy some sort of computational or Oracle efficiency is a really interesting direction for future work. So that's it. Thank you for listening.
Are there any questions?
The algorithm where you also take into account round t-1, like does it help if you look at a few further rounds in the past? Like, do you get better Do you reduce the exponent or you cannot, basically?
Yeah, it's a good question. So you're talking about optimistic hedge?
The first part.
Yeah. So that actually doesn't help, at least like if you do it kind of in the natural way, where you just say,
I mean, I don't know what weights they should have. So
right. So like, I don't think that's been fully explored. And there's like a kind of a general class of algorithms you can study like this. There have been some papers which look at like what happens if you do it in a particular way with certain weights. And they show that you actually don't get any better regret bounds. In fact, they actually get a little bit worse. Like the more rounds you go back, your regret bound gets worse by like a constant factor or something.
So this is for a specific choice of weights or for any?
It's for a specific choice of weights.
I see.
In terms of general choices of weights, maybe you can improve your regret bound by a constant factor. Like in many, like optimistic hedge basically gets, or optimistic gradient descent in general gets optimal rates for most not convex concave problems we're aware of. So like I don't think you'd be able to improve it by more than a constant factor, by lower bounds. But I think it's possible that maybe there's constant factor improvements you can get by.
I thought there was a gap between the lower bound and the upper bound, right?
You mean for
The upper
like
bound
our fast rates, like the log t, the poly log t? Yeah, so that's possible. I think that probably, I mean, this is just a guess, but I think that probably optimistic hedge will get the best. Like, I don't think you'll need to look back further, but it's possible it will. It's a good question.
Okay.
No, you mentioned that if the algorithm has last iter convergence, it helps you in the proof.
Yep.
To get like faster, like smaller regret. Like, can you make this claim formal?
No. I mean, I think it's more like, so the particular paper by Sai et al. That I was thinking of, they have several lemmas, which I think they're both used for last iter convergence and this fast rates. It actually would be interesting to make it formal. That would be a really nice application of last iter convergence. But I think for now it's just that in an informal sense. Really.
Okay, thanks.
So in terms of like contextualizing the literature, why don't these algorithms or the results follow from like sequential or Adversarial complexity notions, or do they follow along this paradigm, or where does it stop? Like,
yeah, that's a great question. So in terms, some of them like I think do. It's like getting the fast rates in the realizable setting. I think you can use sequential Adversarial complexity to get those. The place where like, as far as I can tell, you cannot extend sequential Adversarial complexity is to get this stability property. Basically, to get a learning algorithm that only changes by a little bit from round to round. That's where basically the minimax theory that you use for sequential Adversarial complexities doesn't seem to work. And that's where we need this explicit construction. So I think it'd be really interesting to kind of use that machinery to get these results as well. But we tried and it doesn't seem to work.
thank you.
Right, let's thank Noah again. And we're back at 2 p.m. for the afternoon session and the reception.